Good morning, everyone. Hope you're all doing well. Hopefully nobody lost any trees or anything. We haven't looked for trees. Part of our barn roof flew away last night. It was pretty rough last night. So we are going to finish up chapter 4 today. Your test will still be on Sunday, even though we've had these sort of shortened classes because we gave ourselves enough cushion room, so we'll be able to get through everything. So make sure you are taking your test starting Sunday at 5 a.m., open until Monday at midnight. We meet on Monday, so I will give you another reminder just to say, hey, make sure you're getting your test done. Yeah, you want to be prepping for that. One thing I want to note is that I send emails and such through the announcements. So if you go to our Moodle page, there's an announcements tab here, and you can always click on there to see the announcements, but it should automatically send you an email with those announcements. So if you haven't gotten the announcements about like weather cancellations for the last 2 days, you're going to need to shift your preferences in Moodle so that you do receive announcements. Your test does have to be done in one sitting, yes. So someone asked me, yes, you can't like do a question or two and then decide to go have dinner and look up that question. No, you've got to sit down, take it. So you definitely want to study beforehand. So back to the announcements thing. So if you haven't been getting these announcements, the email should look sort of something like this. Like this here, Chem 092, OT1, class delay 2321. If you're not getting that, you need to go into your Moodle preferences. And then where it says notification preferences, you need to make sure that you have it open or you have it on for receiving emails in any sort of forum. Okay. If you're having trouble with that, just let me know after class. But I want to make sure that you're getting those emails because that's how I let you know things are what's going on. So chapter 4, we left off, we were talking about ions. So cations and anions. And we said, you know, the ion charge is going to be the number of protons minus the number of electrons. So if you're a positively charged ion, it means that you've somehow lost an electron or 2 electrons or 5, whatever it happens to be. Opposite is true if you're negative. If you're negatively charged, on this first one, you see how the electron is sitting on the product side? It means that this thing sort of pooped out or released an electron. Here, the electron is on the reactant side because the electron is being digested by the fluorine. So the fluorine eats the electron up to form an overall negative charge. The ion charge formula is still the same. It's the number of protons minus the number of electrons. In this case, though, it has 1 extra electron or 1 more electron. So the electrons win 9 protons for every 10 electrons or a -1 charge. So we had played around with this and we'll do a little bit more. Okay, so let's say we've got sulfur, and I'm gonna have sulfur just like this. And then I want to look at the sulfur ion. Now, sulfur, go to your periodic chart and find what column it's in. So do you see how it's in column 6? What did you write above that column? Hopefully you wrote a -2 or a 2-. That's because the things in that column will always like to form a 2- charge. So if I was to write it like this, the sulfur ion, and I didn't give you the charge, you would be able to look the charge up from your periodic chart, but I'll give it to you here, okay, 2-. So I want you to tell me the number of protons, and I want you to tell me the number of electrons for each of these. Again, we're gonna leave neutrons off for right now. We'll talk about that in a little bit. All right, so go ahead and do 1 and 2. I'll just give you, 30 seconds. It shouldn't take too long. Okay. So protons, remember, protons are synonymous with whatever the element is. So if it is sulfur, it has to have 16 protons. That is non-negotiable. Can't change that. Electrons can change. Neutrons, which we'll talk about in a minute, can also shift. So electrons, if we're charge neutral, which if there's nothing in that upper right-hand corner, you assume that this thing is charge neutral. And by charge neutral, I mean protons equal electrons. The positive equals the negative. So if I have 16 protons and I'm charge neutral, I better have 16 electrons. Now this one is a little bit different. Yes, they're both sulfur, but this is the ion form of sulfur, 2- charge. So I just think of negative as being electrons. So if I've got 2-, that means I've got 2 more electrons. Electrons should equal 18. Now, if you want to plug it into that little formula, remember charge equals protons minus electrons. So if I know my charge is a 2-. If I know my protons, it's 16 minus whatever my electron is. So this is my variable. Okay, well, subtract 16, subtract 16, I get minus 18 is equal to a negative E, which move the negative over, we get electrons is 18, right? Questions on that? Questions on how to do it for something that is not charged versus something that is an ion or charged? How you're going to know if it's an ion or not, it's going to say sulfur ion, or it's going to have it in the upper right-hand corner. Have you do just one more, just to get a little bit of a bigger number in. Let's do PB 4+. Tell me the protons and tell me the electrons for this thing. And then we'll move on. Okay, so it doesn't really matter how big this thing is, it still follows the same rules. So lead is a bigger element. Its number of protons, it's going to be 82. Remember, this is the atomic number. It's synonymous with whatever the element is. The electrons here, if it's a 4+, that I know it feels like, oh, I'm adding 4, but you're actually going to need to subtract 4 from the number of protons, right? Protons win out. There's more protons than electrons to give you the positive. How many more protons are there? There's 4 more. So I'd take 82 and I'm going to subtract 4, which should give me 78 electrons. Or remember, 4 plus the charge equals the protons, which is 82, minus the electrons. Well, in order to get a 4, this would have to be 78. So moving on, let's talk about neutrons, because what do we know about neutrons? They have the same mass as protons, right? They have the same weight as protons. They live in the nucleus like the proton. How are they different though? They are neutral charged. So they don't balance out a plus or a minus. They don't have any play in making ions. So no charge difference, but they do have a mass, a pretty heavy mass. So when we add and subtract neutrons, it will start to change our the mass of the whole atom, or it'll make it heavier or lighter. Oh, real quick, we already went over this, but +1 for column 1, +2 for column 2. These have varying charges. They can be a variety of pluses. They'll always be pluses though, because they're metals, transition metals. Remember, metals like to form cations. So there'll be some sort of positive. You're never going to see like iron with a negative charge. Doesn't really happen. Remember column 3, we put a +3. Minus boron. Boron is a nonmetal. It's on the zigzag, above the zigzag. It doesn't eat up give up electrons. And we've got -3, -2, -1. And then we've got our noble gases over here that don't do anything. I want you to add a couple more in, okay? There are a couple transition metals that have fixed charges. So aluminum is a 3+, so find aluminum on your periodic chart. I want you to go down and to the left in a zigzag like this. Boom, boom. Okay, so down and to the left, you should hit zinc, number 30. Put a 2+ in that box. And then down and to the left from there, you should hit silver, number 47. That has a 1+ charge. Okay, so aluminum is 3+, zinc is 2+, silver is 1+, 3, 2, 1. Those I will want you to sort of treat as a main group element. So zinc will always be a 2+ charge. Just have that written down. And we'll come back to that more in the next chapter when we get into compounds. Okay, so an isotope. An isotope is when you have the same element, but it has a varying number of neutrons. So there are a few exceptions to this specific rule, such as boron, but that we're not going to talk about that. So all atoms of a given element have the same number of protons, right? So if we're carbon, how many protons do we have? Look at your periodic chart. We have 6. In order to be carbon, you have to have 6 protons. How many neutrons do you have? That varies. Do you see how underneath carbon, you have the atomic mass, which is 12.011? It's a decimal. It's like, why is it a decimal? Shouldn't the mass be a whole number, right? The mass, I'm going to have you guys write this down if it's not already on the slide somewhere. No, it doesn't. I'll just have you write it down. So atomic mass, the mass of the whole atom equals protons plus neutrons. Why don't we include electrons? Because they're so infinitesimally teeny tiny small, they don't really have an effect. So your overall atomic mass will always be the number of protons plus the number of neutrons. So if we look at carbon, carbon has 6 protons, but its mass is 12.011. It's like, well, where is this coming from? Shouldn't it be technically like 6 protons plus 6 neutrons to give you an even 12? Well, this number here, this atomic mass that you're seeing on your periodic chart is the average atomic mass of all the natural isotopes of carbon, because some carbon has 6 neutrons, but there are other types of carbon that instead of having 6 neutrons, they actually have 8 neutrons for a total mass of 14. That's a very small percentage. Have you heard of carbon-14 or radiocarbon dating, where they age things with a radioactive isotope? That's the carbon-14. So the average of these two together will give us this overall mass. Any atom that has the same number of protons but a different number of neutrons, we're going to call an isotope. All elements have a sort of a unique percentage of these natural abundances in nature. So let's look at neon. Neon exists in a couple different states. We have neon 20, neon 21, and neon 22. Do I expect you to have every isotope for every element memorized? No, definitely not. Okay, but you do need to be able to read them. So when you say something like this, neon 20, do you see how this number isn't written in the upper right-hand corner as a superscript? It's not a charge. When I write it as neon with a dash and the big 20, this is saying that for this specific neon, I have a total mass of 20. Now, how many protons does neon always have? Always has 10 protons, right? So in this instance, for this neon 20, how many neutrons do you have? We'll take the 20, subtract the 10 protons. What's left over? 10 neutrons. Okay, 10 plus 10 gives me the neon 20. What if we're instead talking about neon 21? Neon 21 is one heavier than neon 20, right? Am I going to change the number of protons? Never, because it's still neon. So the protons will still be 10. What happens to the number of neutrons though? They bump up by 1. So if I'm talking about neon 21, we would say it has 11 neutrons. And then let's go even one step further. Let's look at an even heavier one, neon 22. Neon 22, it's still neon, so we still have those 10 protons, but the number of neutrons has now become 12. So all of these classified as neon. This one is the heavier of the neons. This is the lighter. Nothing changes with the charge because neutrons are neutral. Now, when we look at the natural abundances, and this is not, again, this isn't something that I would expect you to have memorized. Where do these numbers come from? They're found experimentally. Okay, so most of the neon out there, and in this tube here specifically, this neon light, most of it is neon 20. So for whatever reason, having 10 protons and 10 neutrons is just more effective and stable. So we have 90% out there is this neon 20. Now there's a smaller percentage, but not insignificant, of neon 22. So after neon 20, neon 22 just sort of works better. Then there's a very, very small percentage of this neon 21, 0.27%. So super teeny tiny, but still, you know, in chemistry, we wouldn't say that's negligible. 0.27% is still has an effect. So if I was to take these numbers and multiply them by their relative percentage, I could get an overall averaged mass. Has anyone ever calculated a grade in a class where that you had to like average it out? So your tests were worth 60%, your homework was worth 20%. It's very, very similar to that, okay? You're gonna be weighing out based off of what the percentage is. Let's look at a couple other ways that isotopes are written. So sometimes they're written like this, where you have the symbol, neon. They write the mass number in the upper left-hand corner, and then they write the atomic number in the lower left-hand corner. So these are sitting in front. So it is a superscript and a subscript, but they're sitting in front of the number. This way seems a little redundant to me, specifically because if it's neon, wouldn't its atomic number always be 10? Right? It's kind of like, why do you even have to write that? Neon is going to be always paired with an atomic number of 10. But this is important because this tells me how are my masses shifting or how are the number of neutrons shifting. We already went over this, but the mass number A is the sum of the protons and the number of neutrons. So the number of neutrons in an isotope is the difference between the mass number and the atomic number. Here are some other ways of writing it. Neon-20, I kind of like this way. This is like the most effective way, efficient way for me. Or sometimes they'll write it out fully as neon-20. Remember that these are not superscripts. It's not saying neon with a 20 in the upper right-hand corner, so it doesn't have like a charge of 20. It's writing it as a full number, fully sized number. So you will have to be able to do one of these calculations, and this is sort of what I was saying about it, like averaging your grade. But you're going to need to be able to calculate the average atomic mass of an element. So let's say we look at chlorine. Chlorine has two naturally occurring isotopes. There's chlorine-35. Now, sometimes in these problems, they'll put in parentheses a very specific mass. So they're calling it chlorine-35, but it's really 34.97. Use that number, all right? If they don't give you this number, like let's say this wasn't here and it just said chlorine-35, you could just use the value of 35. But if it gives you a more detailed number, use the more detailed number. So chlorine 35 makes up a majority, or 75.77% of the chlorine. The remaining 24.23% is made up of this thing called chlorine 37, which actually has a mass of 36.97. Okay, so we're going to want to use that number. So most of it is chlorine 35. So just like common sense wise, if I have chlorine 35 and chlorine 37 and 75% of it is chlorine 35, I know when I average these together, my number should sit closer to 35. Now, what people like to do is oversimplify this, and they'll sometimes say, oh, I'm just going to take this number and add it to this number and divide it by 2. You can't do that because it's not a 50-50 ratio. If it was a 50-50 ratio, you could do that. What we have to do is take into account that this is 75% and this is like 25%. So first of all, what is a percentage? Percent, cent being like a century or a penny, per 100. So we need to get out of percentage, or we need to take whatever the percent is and divide it by 100. So you'll take this value, divide it by 100, which is the same thing as moving the decimal over 2 places. All right, same thing with this. Take the percentage and move the decimal over 2 places. So we have 0.7577 and 0.24239. Now to calculate the average atomic mass, you're going to take the percentage, unpercented, you're going to multiply it by the mass. So we take this number here, we multiply it by this number, and then we add it to the second isotope. So we take the percentage of the second one, and there's a formula on the next page that I'll show you guys. But we take the percentage and we multiply it by the mass, and we just add those together. Now, what if you had 16 isotopes? How many things would you have to add together? 16. Am I going to give you 16 isotopes? No, I'll probably give you 2 or 3. So you multiply the 2 values together. So this is for isotope 1. And again, we'll do an example here. So you don't have to write all this down if you don't want to. But this is isotope 1, and this is all information on isotope 2. So you multiply first for each of them, and then you add them together. And what we end up getting is 35.45. And if you look at your periodic chart for chlorine, the mass is 35.45. That's why the number isn't a whole number, because some of it's 37 and some of it's chlorine 35. So let's look at a neater version of this. This is the formula. So you take isotope 1, you take the fraction of isotope 1, the fraction being the decimaled out percentage. So move the decimal on your percent over 2 or divide it by 100. You multiply it by the mass, and then you add it to the next set of parameters for isotope 2, add it to the next one for 3, 4, 5, 6, all the way down. So I think it's much easier to just try it. So I'm gonna have you guys work on this one here. Gallium is a metal that has 2 naturally occurring isotopes. So there's gallium-69, and look though, it says with a mass of 68.925. So use this as your mass number. Even though it's gallium-69, use the more detail. And this is a natural abundance of 60.11%. And then there's gallium-71, but it actually has a mass of 70.9247. Again, use this number. And its abundance is the remaining 39.89%. Calculate the averaged atomic mass. Okay, so 2 isotopes. We got isotope 1 and isotope 2. I'm going to give you guys 4 minutes to set it up and calculate it out. And then we will come back together, go over it. Okay, so 2 isotopes. So we'll be adding 2 things together. The first thing I like to do with these problems is get rid of my percentage and get it into its fraction. So 60.11 divided by 100, or it's the same thing as moving the decimal to the left too, undoing the percentage. So these will be our 2 weights. We're going to multiply those by their corresponding masses. So for this first one, what was the 60% or 60.11% is multiplied by the more detailed mass of 68.9256. Again, if they didn't give you this more detailed one, you could just take that and multiply it by 69. That would be fine. And then we're going to add it to the remaining percentage times its corresponding mass, which is the 70.9247. So you'll get 2 values as AMUs, and then we're going to add them together. They rounded here to 4 significant figures. I'm not going to be super anal about rounding to the correct number of sig figs. Why is it 4 sig figs here? Because when you multiplied these together, this had 4 sig figs, this had 6 sig figs. So this number you really only honor to the 4 sig figs or to this decimal place. So it's giving you 2 decimal places. Any questions on that outside of we'll do another example? No? Okay. One thing I do want to talk about, so with isotopes, because you may have heard things like radioactive isotopes. So there's 2 types of isotopes. There are stable isotopes and there are radioactive isotopes. Stable isotopes are stable, so they don't decay. So carbon-12 is an example of a stable isotope. It isn't going to like break apart its nucleus. Carbon-14, on the other hand, it has 2 extra neutrons shoved in its nucleus, and that makes the nucleus sort of unstable. So it wants to break apart or decay into simpler things. So whenever something decays, it releases radiation, nuclear radiation, which is a lot of energy. And these are known as radioactive isotopes. This is what you find in nuclear power plants or radon in your basement or things they use for radiation for treating cancer or atomic bombs, right? These isotopes that are unstable that want to break apart. A lot of times they're bigger isotopes. Some of the heavier isotopes tend to be more unstable because they have clunkier, bigger nucleuses. But some of the smaller ones can be unstable as well. So, okay. So benefits of isotopes. This talks a little bit about isotopes. That's great. I'd rather spend time doing another example problem with isotopes. And then that's everything. That will be covered on the first test. All right, so chapter 1, 2, 3, and 4. Chapter 1, again, that's sort of like a for your information. That's like your intro to chemistry. I'm not really gonna harp a lot on chapter 1. So it's mainly gonna be chapter 2, 3, and 4. When you are ready to take the test, let's say you wanna take it at 5 a.m., you will just click on this link. And once you get started, it'll open up and then you have a given amount of time. Usually it's an hour and 30 minutes, I believe. Yeah, you have an hour and 30 minutes. Sometimes what people do is they'll think, oh my gosh, it's an open book, open note test. So I don't need to study. I'll just kind of do it on the fly. Don't do that because you can get stuck with having to teach yourself chemistry while you have an hour and a half and that clock is ticking down and you're like, oh my gosh, I don't remember how to do this. Don't do that to yourself. Just study. That's the point, study. Even though we're online, study. Okay, let's do, oh gosh, zoom in here a little bit. Let's do this one just because it's so much fun. Titanium has 5 common isotopes. Titanium 46 is 8%. Titanium 47 is 7.8%. Titanium 48 is 73.4%. Titanium 49 is 5.5%, and titanium 50 is 5.3%. What is the average atomic mass of titanium? I want you to notice they don't give you a more detailed mass for these, so don't stress about what number to use. Just use the 46, the 47, the 48. Try and zoom in here a little bit more. There we go. Whoa, there you go. I'll give you all like 4 minutes again, 3-4 minutes to work on that, and then we'll go over it. And please, if you have any questions while we're going over this, throw it in the chat. Or you can even turn your mute off and I can try and help you out because I want you to be able to do this. I don't, and if you understand it now, then you won't have to study so much later. Okay, so 5 isotopes. When I do this, I like to stack mine one on top of the other as opposed to like making them in a big line. I don't know, like it's a little bit neater. So the first isotope is this titanium 46. So I'm going to take the mass 46 and I need to multiply it by the percentage divided by 100. So I move the decimal over 1, 2. So it should be 0.08. All right, so this first isotope has an overall weight of 3.68. All right, the next isotope is 47 times 1, 2. That would be 0.078. And this is 3.666. I'm going to keep as many decimals as I can. The next one is 48 times 0.734. So that's the big guy. That should be the biggest weight. 0.734. This is 35.232. We've got 49 times the 0.050. Make sure you're moving the decimal over 2. Okay, sometimes people will just move it over 1 and say, oh, it's 0.5. I'm sorry, this is 0.55. 0.055. So 49 times the 0.055, and that gives me a 2.695. And then the last one is 50 times 0.053. And this is equal to 2.65. So all these numbers are small, right? But when I add each of them to each other, I should end up with a number that averages somewhere between 46 and 50. If your number is smaller than 46 or bigger than 50, you have done something wrong. My guess is you didn't move the decimal over twice on your percentage. Because if I took 46 and multiplied it by 8, I would end up with a large number, right? These numbers would be really big. So make sure you're multiplying it by the correct thing. So we'll take that 2.65 plus the 2.695 plus the 35.232 plus 3.666 plus 3.68. And I ended up, when I add all of these together, I get 47.92 AMU. I like that. It's like sitting somewhere in the middle of these numbers. If you got 47.93 or something like that, that's okay. It's close enough. So yeah, that's how you do it. So if you can do that, you can definitely do one with just 2 or 3. Any questions? Okay, well then we are done for the week. Make sure you get your labs, homework, tests going, and I will see you on Monday. Hopefully we don't have any cancellations anymore from weather. We'll just do the best we can. All right, so have a good weekend. Bye, everybody.